I am pleased to introduce our first speaker, Professor Igor Bray. Igor ranks in the top few in the world in the field of atomic and molecular collision physics and is responsible for several major paradigm-shifting research breakthroughs during his career. Welcome, Igor.
Thank you. Good morning, everyone. Ordinarily, I would begin by thanking the organisers of the meeting for inviting me, and I guess this is no different. Thank you so much for all the people who made this happen. It is a phenomenal honour, and it is my great delight to be here. I was also delighted to hear how all of us are so grateful to the teams that we work in, and Andrew said earlier that the chemists hunt in packs. Well, the truth is all of us hunt in packs, just that the packs are bigger in some cases than in others. Now, the talk that I'm going to give this morning is one I give at high schools, and I go and tell school children to consider a career in science for the people you will spend your life with. And that's how I begin, and then I explain what it is that I do. So I work in atomic and molecular collisions, and today I hope just to tell you a bit as to what they are and what we can do with them. So I'm sorry we don't have enough time to show you all the animations I would show at schools, but I'm going to try and fit this in just 10 minutes or so. So collisions on an atomic scale go on all around us in this room right now. We have collisions between the molecules of oxygen and nitrogen, and that's what causes the temperature. And of course, without those collisions, we'd have a temperature of absolute zero and freeze and die. So collisions are a wonderful thing. They are very, very useful, and their quantitative understanding has immense applications in many areas. And all chemical reactions are examples of such collisions. But fortunately for us, they're very difficult to calculate. If something is difficult, that's good, because that means that we'll get in there and we'll hopefully be the first one to solve them. First of all, they're governed by the laws of quantum mechanics. So we cannot calculate individual reactions, we can only know the probabilities. Then there's lots of infinities involved. There's countably infinite discrete spectrum of atoms and molecules. There's an uncountably infinite target continuum. The charged particles mathematically continue to interact at infinite distances. In fact, quantum mechanics was not formulated until our work in the around the 2007-10 period. Just quantum mechanics for collisions was not rigorously formulated. And there can be multi-centered. If you think of molecules, they have many centers that come interact, lots of centers involved, which makes the calculations particularly difficult. And of course, computers don't like infinities. And so it's our job to set things up in such a way that we can solve these particular problems. And we developed this method called the convergent close coupling method, and to date it's still the only one that is valid for all energies and for all collision processes that you have in these collisions. So what are the applications of our work? Well, in our case, we know all of the particles involved. We know all of the forces involved. It's primarily the Coulomb potential that is the source of interaction. So the new physics arises from few body behavior. After all, life is an example of simple particles coming together. Take enough of them and you have human beings. So there's a lot to be learned in few body systems. So our primary motivation is to be useful. Right? And in order to be useful, you have to provide accurate data. So we've made a decision about 30 years ago, we will either do things properly or not at all. And that has served us well. So the first application. The biggest project on the planet is this reactor called ITER, International Thermonuclear Experimental Reactor. It is now being built in Cadarache, France. And the goal is to replicate the core of the sun here on Earth, but not get sunburned. And the idea is to get the temperatures so high, in fact hotter than the core of the sun, to overcome the Coulomb repulsion barrier between the heavy nuclei, bring them together and fuse. The fuel source is just seawater, and it is very, very clean, but it is the most dense energy source known to mankind. And here in the middle is a very, very high, millions of degrees in the middle here, and absolute zero only a couple of meters away. And this is an incredible machine. To see its scale, I don't know how well it comes across, but this is a person here. Right? Now, at this point, you say, wow, because that's what the kids would do, but never mind. And and our job is to calculate all of the reactions that go on inside here. So it's collisions between atoms, molecules, whatever's in the wall, things will be hit, and there are a lot of sources of energy losses. The idea is you have to provide enough energy so that you can ignite the plasma and get into a self-sustained situation. The goal of this instrument is to generate 10 times more energy than what you put in. If that works, and we will know that in around the mid-2020s, then the next reactor called DEMO, its job will be to generate electricity. So that's at about $30 billion worth, is the biggest project on the planet. The next area that we work in, the second largest scientific project on the planet, is the Large Hadron Collider at CERN. Apart from getting Nobel Prizes for discovering Higgs bosons, they're also interested in creating neutral antimatter. Why? Because there's a couple of Nobel Prizes going there as well. If anyone can explain matter-antimatter asymmetry in the universe, there's a Nobel Prize there. If anybody can combine quantum theory with gravitation, then there's another Nobel Prize there. What is the goal? The goal is to create neutral antimatter, measure its spectroscopic properties to understand what the difference is between, say, ordinary matter and antimatter, and also do a very simple experiment. See how it behaves under gravity. If you create a neutral an anti-hydrogen atom and drop it, nobody can tell you what will happen. Will it fall like ordinary hydrogen? There are theories that say no, it might even rise. So how do we come in here? So apologies for this rather complicated slide here or figure. So we have positrons. So why CERN? Because that's the only place you can get a beam of antiprotons. Okay, you eventually bring in positrons here. You create positronium. This is an exotic atom of a positron and an electron bound together. You laser excite positronium to get into a highly excited state. You bring in antiprotons with highly excited positronium, and out pops an anti-hydrogen beam. Where do we come in? Well, we give the calculations that show what the relevant states should be to maximize your yield of anti-hydrogen. In December this year, there was a paper in Nature that they've made enough anti-hydrogen to measure its spectroscopic properties, the 1s to 2s line, to 10 significant figures. And unfortunately, those 10 significant figures are the same as the first 10 significant figures of ordinary hydrogen. But we still have 5 more figures to go. For ordinary hydrogen, it's been measured to 15 significant figures. What an extraordinary achievement. And they want to do that for hydrogen, they want to do that for anti-hydrogen. Next application is astrophysics. This is a picture of the Chandra Space Telescope. There you have, where it looks at for X-rays, where X-rays come from in space. Well, it turns out they come in from charge exchange collisions. That's how they discovered water on comets. Somebody said, let's look at, with Chandra at the comet. People say, that's crazy. Comets are cold. Where are you going to get high-energy X-rays coming from? Well, it turns out solar wind provides a highly charged ions. Those ions interact with molecules on the comet. They rip electrons from those molecules and pick it up into a highly excited state of the ion. Then that ion decays and emits an X-ray. And the extraordinary part that from those X-rays, series of X-rays that come out, you can work out what was the projectile and what was the target. It's a phenomenal experimental achievement, and that's how they found water there. And our job is to calculate these particular collisions. They're multi-center collisions. We used to have a center of excellence for antimatter-matter studies, and what we have learned from positron scattering on atoms was readily applied to proton or positive ion scattering. I would go around saying that ions are just heavy positrons. We're also working with lighting industry. We actually got some money from Osram Sylvania to help increase the efficiency of the fluorescent lighting system. When you see a fluorescent lamp, you can think of it, all it is electron scattering on mercury. And we have the world's best theory, both relativistic and non-relativistic, for the description of lights. It seems that we may not have backed the winner here. The solid-state lighting is progressing particularly well, but it's nice to see that we went from incandescent lamps, which are about 5% efficient, to fluorescent, which are around 60%, and maybe solid-state going up towards 70%. And last couple of applications is in the medical areas. Most people are familiar with PET scans, that's positron emission tomography. There you image cancer with the usage of positrons. The patient ingests positron-emitting isotopes. Rapidly growing cancers preferentially absorbs those sugars that have the positron emitters associated with them. And those positrons come out, slow down through interactions, form positronium, it annihilates, creates gamma rays, and measuring gamma rays in coincidence, you can go back and work out where your cancer is. And our job is to calculate positron stopping power in the soft tissue to be able to accurately put the boundaries on and improve the quality of PET scans. And why do you want to know it very accurately? Because when you know where your cancer is, you can treat it. There's a new modality called proton therapy. And in fact, in May's budget, it was announced that Adelaide's getting $68 million to build the next facility. That's fantastic for us. I only found out about a week or so ago. What's the issue here? Well, on the right-hand side, we'll have conventional X-ray radiotherapy. X-rays kill the cancer, but they kill everything else as well. And so there's a lot of side effects with conventional X-ray therapy. The beauty about proton or ion therapy is that due to the work of William Bragg, an Australian Nobel Prize-winning physicist, I think he got the Nobel Prize in 1905, he showed that heavy projectiles deposit all of their destructive energy just towards the end of their travel. This is phenomenal, because if you can get your calculations just right, you can deliver the destructive energy of your ions right to the tumour without the side effects, without the extra dose here. You can see here there's no extra dose at all and hardly any damage at the front, but only if you can get the calculations right. Thank you very much for your time.
Thank you, Igor. We have time for one burning question. No questions. Well, it was totally understandable to everybody.
Thank you.
Thank you.
Thank you.
Thank you, Igor.